So we just want to talk here about some properties of definite integrals. These are some things that you should kind of keep in mind as you're doing these integration questions. They can sometimes make the question a little bit easier. So the first one is, what if you have an integral from a to b of a constant and you're integrating over x? Well, if you're integrating over a constant, this integral is just going to be the value of the constant times b minus a. And this makes sense if we think about it sort of geometrically. We imagine what our graph of our function looks like. It's going to be a constant c. If we're integrating from a to b, what does the integral represent? Well, it represents the area underneath the curve. The area underneath the curve here is a rectangle. What's the area of a rectangle? Well, it's the height of the rectangle times the width of the rectangle. The height is just c. The width is the difference between b minus a. So this integral kind of makes sense here. Okay. Another one is one that I've mentioned before in terms of, that's the sum of the difference rule for doing integrals. If I have something, if I'm doing the integral of two functions that are added or subtracted, okay, I can always think of this as being two separate integrals added or subtracted. So I can do the integral from a to b of f at x dx plus or minus the integral from a to b of g at x dx. And you're going to use this rule almost without thinking about it, breaking up a series of terms and doing the integrals piece by piece. Another one to keep in mind is that if we have, sorry, this is number 3 here. If we have integral, again, from a to b of some function, f at x dx, and we interchange the limits of integration. So instead of integrating from a to b, we integrate from b to a. Okay. The values of the integrals are going to be same, except the sign is going to be opposite. So when we reverse the limits of integration, we just reverse the sign on the integral. And sort of the explanation for this is, if we think about what this integral represents in terms of a sum, we got this integral by doing the limit as x goes to infinity of the sum from I equals 1 to n of f at xi times delta xi. Okay, this was basically our definition of what this integral actually represented. And in this, delta xi, the width of one of our little rectangles that we were creating underneath our curve, was given by b minus a over n. Basically our end point minus our start point divided by the number of rectangles that we had decided to put in there. That's how we determined the width of each one of those rectangles. Well, if we reverse a and b, we are going to end up with a minus b over n, okay? Which is going to be the same thing. It's going to have the same magnitude, the same number as delta x over I, but we're just going to get an opposite sign, okay? And that opposite sign, that negative sign, is going to carry through all the way through our entire integral here, okay? So reversing limits of integration changes the sign on your integral. What if we are integrating a function, f at x dx, and instead of integrating from a to b, we're integrating from a to a. So our two limits of integration are exactly the same. What do you think that is going to equal? What do you think, Daphne? 0, yeah. We can imagine this in terms of a rectangle of some width. It's going to have 0 width because Again, if we think about it in terms of this sum, how wide is each one of these rectangles that we're putting under there? Well, if we do a minus a over n, the width of each rectangle is going to be 0, so we're multiplying up here in this sum f at xi by 0, which is just going to give us 0 all the way through. And the last one that is kind of useful sometimes is, let's say we have an integral where we are going say integral from a to b of f at x dx. We can always take that integral, or this range of integration from a to b, and we can break it up. Okay, let's say there's a point C somewhere between a and b. We can do the integral from a to c f at x dx and add it to the integral from c to b f at x dx. Okay, so we can break a large integral into two smaller integrals. And this makes perfect sense if you think about it graphically. If I've got some function like this, this is my f at x, I want to integrate from a to b, but instead I've got some point c in between. My integral from a to b, okay, this entire red area under here, is of course going to be the same as the integral from here to here, from a to c, plus the integral from c to b. All right. Now, where this becomes really handy is if your function does something interesting at that point c. You could have a function that goes like this, okay? And you want to integrate from a to b. You might decide, hey, it's useful to figure out what that point c is where it crosses the x-axis and divide this integral into two parts. The integral from a to c and the integral from c to b, because the question kind of divides naturally at that point. Okay? So those are 4 things to keep in mind, and we're going to be using some of them later today.